All right. So, hello everyone. My name is Lohit Pal, and this is the live session, third live session of Introduction to Interfacial Webs. So, in the last class, we have talked uh, about some more linear oscillator problem, and we have used normal mode analysis to solve those problems. So today onwards, we will now try to solve uh, we will we will try to solve the nonlinear oscillator equation. So in the last class, just a second, let me join from my tab as well. Okay, so let me share my tab screen. All right. So we are ready now. So all right. So today our target is to find a solution of the nonlinear pendulum equation. So as I told in the last class, sir, what is the equation for that for the nonlinear pendulum? So yeah, I will share this class note with you. Okay. So for the nonlinear pendulum, so this is the governing equation. This is the governing equation for your nonlinear pendulum. Okay. Now we will try to. So in our class two course, we always take the assumption of. Okay, just a moment. So in our plus two course, we always try to solve the problem taking the assumption that theta is small. When theta is small, then sine theta is equivalent of theta, and you can very easily solve that problem. Okay. But now we will try to solve the complete nonlinear problem. Okay. So in order to do that, we need to use something that is called Jacobi elective function. We have to we have to take help of this thing. So now what is this? Okay. So now, before going into Jacobi elective function, just refresh our memory of the simple trigonometry. That is, so suppose this is your circle, okay, and suppose this is the center of the circle, okay, and this is some angle. This is suppose theta, okay, and the radius is r. So if you take projection, then this distance is x and this distance is y. Okay, so then sine theta equal to y over r, cos theta equal to x over r. Okay, so this is the basic trigonometry, and we know the identity of using sine theta, cos theta, and everything. Now, in order to solve the problem in the full nonlinear pendulum problem, we need to do something similar, but it is more complicated. So we will now try to take some take some no, we will now take an ellipse, and we will like to measure some angle which is similar to sine theta and cos theta, but obviously it is as it is ellipse, so it is obviously different. So suppose this is your ellipse. Okay, this is your ellipse. It has major axis of length a and minor axis of length 1. So what is the equation of the ellipse? This is the equation of the ellipse. X square plus a square plus y square by 1 square equal to 1. And from your school level course, you know that here what is this? This is the eccentricity. Okay, k equal to square root of 1 minus 1 by s square. Now now we have to define a similar kind of function like this, and that we define the function. This is not exactly theta. We will define the function like u. That this it is already discussed in class. It is this r d theta. Okay, that is which is this amount of length. Okay, we will define this u as r of integration of r d theta, something like that. Okay, now for the for this elliptical geometry. So what is your so similar to sine in this elliptical framework, it is Sn. Okay, and remember this is u, not theta. Okay, so similar to y over r, it is say Sn of u and k. Remember that it will be a function of both u and k. Okay, because the shape of the ellipse depends on the eccentricity. Okay, so that's why Sn is function of u and k. Sn is similar to sine, and similar to cosine, there is Cn u by k. Here this distance is x, as this distance is y, and your Cn uk is x over a. A is this whole length, and dn uk, this is there is no trigonometric analog to this function dn. Definition of dn is r over a, r by a. Now remember that when a equal to 1, okay, that means it will be a simple sphere. So then k equal to 0. So in the limit k tends to 0, your Sn will be converted to sine and Cn will be converted to cosine. Okay. All right. Now let us try to prove some identities using. Okay. So now let us try to prove some identities using this Sn, Cn, and Dn. All right. Now, okay, just a moment. Just a second. Okay. So now your equation, your equation of the pendulum is this: x square by a square plus y square equal to 1. Now your Cn of u. Now I am not using k. Okay, k is constant. K is assumed constant for this case. So Cn of u is your x by a, and Sn of u equal to y. So simply cn square u plus sn square u equal to x square by a square plus y square equal to 1. So this identity is valid. Okay. Now, if you modify this equation, if you add x y square by s square and subtract it, okay, you will get x square plus y square. So remember the image. Okay, this is r. So r is obviously x square plus y square. Okay, so it will be your r square by s square, and it y square, and this is k square. And when what is r over a, so dn of u is your r by a. Okay, and y is sn of u equal to y. So dn square y plus k square dn square u plus k square sn square u equal to 1. Okay, so this is another identity. Similarly, you can find relation between dn and cn as well. You just need to substitute sn square u equal to 1 minus cn square u. Okay, so you have got total three identities. All right. Now, hmm, now, so now we need to find the differential relationship between S and Cn. So what? So I want to say that what is the result of this? Okay, in terms of Cn, Sn, and Dn. So let's try that. So now, suppose so this is a part of your ellipse. Okay, so sorry, my pardon, my drawing is really bad. But if this is your okay, so let's try to do it properly. Theta, x, y, and this is r. Okay. So now from this we can say that d theta. So what is theta? First of all, theta equal to tan inverse y over x. This is true, right? This is true. This is coming from our basic idea of trigonometry. So this imply your d theta. What will be your d theta? It will be 1 over 1 plus y by x whole square into by x square x dy minus y dx. This will be the result. If you simplify it, you will get this expression. Okay. Now your d theta equal to x dy minus y dx by r square. Now remember, in case of this elliptical function, so the angle is not d theta. The angle is du, and du is your r of d theta. Okay. So you multiply both sides by r. So finally you get this is your du equal to x dy minus y dx divided by r. Okay. Now we are ready to differentiate SNU with respect to u. Okay, so let's do that. I have already done it, but let's just erase this. Okay, let me do it again. Okay, so ddu of SNU. The idea is very simple. What is the definition of SNU in terms of x and y? SNU equal to 1. So you have to basically do dy of du. Now, you need to find some functional relationship of y and u. So how to do that? So we already know what is du, right? We know that du equal to x dy minus dx divided by r. So we can write it. Now du equal to x dy minus y dx divided by r. So equal to, so from here we will get r dy minus x dy minus y dx equal to r divided by x minus y dx dy. Okay, why we can write it? We can write it because dy dx into dx dy equal to 1. Okay, now this is not simply this is not the simple division. Okay, this is not like this dx dy dy. No, this is true when yx is an invertible function. Okay, this is true when yx is an invertible function, and you will see that our y is really a good function, so it is invertible. So what is the our equation? We have only one equation, that is x squared plus a square plus y square equal to 1. Hmm? So x by a square dx plus y dy equal to 0. This implies dx dy equal to minus of a square y by x. So if you substitute this here, what you will get? It will be, the result will be, so d du of Sn of u, it will be r divided by x plus a square y square by x. So equal to x divided by x time r, x square plus a square y square. Now from the equation of the ellipse, you will get that it is xr by x square equal to x by a into r by a. So it will be Cn of u multiplied by Dn of u. Similarly, you can find relationship for Cn, dd of Cnu. So you can find what is ddu of Cnu and ddu of Dnu. Okay. Now this is easy. This is just similar. So let's do this. So I have done this for the CNU. You can find the result. Okay. I will not share it again. I will share this script with you, and let's try to do this. So what is dn of u? Dn of u is r over a, right? So it is 1 by a dr du. Now what is du? Du is x dy minus y dx divided by r equal to 1 by a r dr x dy minus y dx. Okay, now you have to do some manipulation. What can be the manipulation? It is r square equal to x square plus y square. So r dr equal to x dx d plus y dy. So what will be the result? The result will be 1 by a x dx plus y dy x dy minus y dx. So it will be now, if you divide it by, let's divide it by dy because we have the result of dx dy. Okay, so it will be 1 by a times x times dx dy plus y x minus y dx dy is equal to 1 by a into 1 by a into mm, dx dy minus a square y by x. X into minus a square times y by x plus y by x plus a square y square by x. So it is equal to x gets cancelled, 1 by a into y into 1 minus of a square, right? Divided by, so x will be multiplied over here, x square plus a square y square. Huh? So this is equal to 1 by a into, so this is a square, right? So if you divide it, if you put it inside here, it will be 1 minus 1 over a square. So it is, so finally it will be x by a into y into 1 minus 1 by a square. So this is, so you can see that this is Cn of, this is Cn of u, this is Sn of u, and this is k square. So d du of dnu equal to k square Cnu and Snu, right? Okay. Now, so and now the, so I will not go over this. So if, so it is discussed in it is discussed in lecture really well, but I will just give you just a brief outline. So if ddu of Cnu and dnu, huh, so you can express Cnu, so using the identities that we have proved earlier, you can convert it to like this. So Cnu is square root of 1 minus Sn square u, and dnu is square root of 1 minus k square Sn square u. So you can write in this way. You can define t as Snu, t is some dummy variable, and substitute it. So your u will be Sn inverse of t. So finally your result will be something like this, and using this you can find the inverse of this Sn. Okay. Similarly, you can find inverse of Cn and inverse of Dn. Now we will use this idea to find a solution of this problem. Okay, so let's do that. Just a moment, I will be back in a couple of minutes. Yeah. Sorry for the interruption. So, so now we will try to understand how to solve this problem. Okay. So this is your equation of the nonlinear pendulum. All right. So No, so in the last class, so I have talked about how to get an energy equation from it, and we have learned that this will be your finally the energy equation, and if this is your initial condition is theta zero is theta zero, theta dot zero equal to zero. As this is constant, so it will be equal to your initial energy, right? So so after a small manipulation, you can write this in this fashion. Okay. Now you can substitute, you can do some modification. You can take sine theta by 2 equal to z, and z, and just do this modification, and finally we'll get the result like this. Okay, and you after some substitution, you can very easily see that it is related to Sn. Okay, so it is discussed in the class in detail. That finally you will get your equation as the form of Sn with some omega t plus some constant k, something like that. Okay, you will finally get that expression of your expression of your total evolution. Okay, so I will not go through the entire calculation. Okay, but let us solve some problem from the assignments. Okay, all right. So let okay. So suppose you are provided with an equation that is d square y by du square equal to 2k square minus 1 y minus 2k square y cube. Okay, and you are provided with four possible solution. Okay, so solution A is y equal to sin h u, b is n uk, c y equal to cn uk, d y equal to cos u. So obviously, very you can see very easily that these two, they are not the solution, because this is a linear solution, this is a linear solution, but there is y cube. Okay, so these two are not the solution for this differential equation. Okay, now let's start with cn of uk. Now what is the identity? ddu of cn u. I am not using k. So we haven't done it explicitly, but this is a chance that we can do it. So what is Cn of u? Cn of u is your x over a, right? It will be 1 by a dx du, and what is your u? Du is your nothing but 1 by a, so x dy minus y dx divided by r. It will be r times dx by x dy minus y dx. So you can write as r by a into 1 by x dy dx minus y. Now what is your dx dy? We have written it somewhere. Just let me check. So your okay. So dy dx is this minus x by y square. dy dx equal to minus x by y square. So equal to r minus, you can take the minus outside, into 1 by x square by y a square plus y. So you can multiply numerator and denominator by y. So you will finally get minus r over a into y by x square plus a square plus y square. Now this is the equation of the ellipse. So it will be minus, it is 1. So it is minus r by a into y. So ddu of CNU equal to minus r, sorry, it is minus SNU DNA. Okay, so this is your identity. Okay, so now what we can do, so let us use some other identities. Okay, so one we can use Cn square U plus Sn square U equal to 1. We can use this identity. And the other identity is uh, Sn square U plus k square dn square U equal to 1. I think I am writing this correct. Ah, no. Dn square U plus k square Sn square U, right? So k square Sn square U plus dn square U equal to 1. So what we can do, we can actually substitute this. Okay, let's see what we can get here. So instead of SNU, we can write, so ddu of CNU. So here we can write this as square root of 1 minus Cn square U, and we can expand it like this, k square into 1 minus Cn square U plus dn square U equal to 1. This implies dn square of U equal to 1 minus k square plus U. So it will be 1 minus k square plus k square Cn square U. Okay, so it will be into 1 minus k square minus 1 minus u. Okay, so now we can actually substitute this CNU with some z. So it will be dz du equal to square root of 1 minus z square into 1 minus k square plus z square. Just a moment. Actually, let's not do in this way. What you can do, you already have the relationship of dsn du and ddn du. Let's use that. Okay. So what I am saying, instead of substituting sn and cn in terms of cn, you can directly differentiate it. Okay, and I think that will be much easier. So if you just do that, or so it will be d square du square cn of u. Hmm? So it will be, what will be the result? It will be minus of, so so it will be dnu. So just use the simple chain rule. ddu of snu plus snu into ddu of dnu. Remember that we have already proved these identities. So it is minus dn square u into cnu, right? Because ddu of snu is cnu into dnu plus snu. Now I have forgotten what is this result. Let me just check what is ddu of dnu. So it is minus k square cnu times snu into minus k square snu cnu. Now I can use the identities. Now I will use the identity. So it will go. So it will be. So what will be the result? It will be plus k square cnu sn square u minus cnu dn square u. So I can take cnu as a common. K square sn square u minus dn square u. So what we can do, we can just simply substitute this, say Sn and Dn, okay, in terms of Cn. So Sn square u, it will be Cn u into k square into 1 minus of Cn square u, and minus Dn square u. Dn square u is 1 minus k square Sn square u. Square is minus 1 plus k square into 1 minus Cn square of u. So equal to Cn u 2k square 1 minus cn squared u minus 1. So if cn u equal to y, I get d square y du square equal to 2k square. So 2k square minus 1, 2k square minus 1 y minus 2k square y cube. So you see, so your y equal to cnu is a correct solution. Okay, all right. Now there is another interesting problem. Let me first write it down. So, so you need to find the the correct expression of Sn u plus v. What is the result? You are provided with four options. That is Sn u, Cn v, Dn v plus Sn v, Cn u, Dn u by 1 minus k square Sn u k square Sn square u Sn square v. So this is a very complicated expression. Okay, you are just expanding it and you are getting this complicated term. Option B, Sn v. Okay, I think instead of writing this, I will just share the screen. Okay, just hold on a second. Okay, so you need to you need to find the expand the result for this. Okay, so you are provided with four options. This option A, option B, option C, and option D. Okay, now, all right. So this is your assignment problem. The second assignment problem. Now, how to deal with it? Okay, now I think I can just stop sharing this screen. Let me share my tab again. Okay, now we do not have any formula. Now we do not have any formula to find an expression for this. Okay, so what will be our choice? So if you see those options carefully, so what we can always do, we can always go back to the trigonometric limit. That means we can go to the for go for the circle. Okay, circle indicates us k equal to 0. That means what is your k? K is square root of 1 minus 1 by a square. When a equal to 1, k equal to 0 implies that ellipse now has become a circle. Now when k equal to 0, your Sn is just sine and Cn cosine and dn is your 1. Okay, because what is a dn? Dn of u is your r by a, remember? And for the circle r equal to a, so it is 1. Now in that limit, if you test this, if you test your result, okay, so what is sine u plus v? It is sine u cosine v plus sine v cosine of u. Okay, you know this. Now if we substitute this at k equal to 0 limit, okay, that means it should be true for the k equal to 0 limit, but because there is no restriction on the value of k, right? So it will be snu cnv. That means sin u cos v dnv is always 1 plus sin v cos u into dnu, that is also always 1. Okay, divided by k square is 0 divided by 1, right? So you will see that this is the correct expression. Now if you do this exercise on the other options that are provided, you will find that none of them are true. Okay, so in this way, if you get some questions like this, you can always go back to your circle, the limit of your circle, and you can find that correct expression. Okay, so this is your correct expression. Okay, all right. Now we can do some other problems as well. So let's do those. Okay. So what we will do, we will solve one more complicated problem using this elliptical function, Jacobi elliptic function. But before that, let us do some simpler problem. Okay. So suppose in the last week, so in the third week, you were taught about the perturbation technique. So what is that basically? So in the very simple sense, that is, you have an equation like x square minus 6x plus 5 equal to 0. You have solution equal to x equal to 1 and x equal to 5. These two are the possible solution. Now if you part up this means, if you suppose instead of 6x, if your solution is minus 6.000, not 000, not 002 x plus 5 equal to 0, then what is your solution? Can you guess your solution from this? Can you estimate your solution from this? So this is your task. So this is called perturbation technique. In simple language, perturbation technique is perturbation means nothing but small change. Okay. Now you have already learned how to tackle these problems. Okay. So what can be the result? So how to tackle this? So you can always take this as 6 plus epsilon, where epsilon is equal to 0.002. This is a small parameter, so perturbation theory should work. So now your expansion is my so we can take an expansion like this, x equal to so what are the two solutions? One is 1, another is 5. 1 plus epsilon x1, okay, plus order of epsilon square. Let's stick to the order. Let's stick to the order epsilon order. That is a linear order. Okay. So another solution may be 5 plus epsilon x1 tilde. So this x1 and x1 tilde may be different or may be same. I don't know that. So, but in general they should be different. So it is x1 tilde plus order epsilon square. Now if you substitute this here, okay, not here, this equation. Okay, now epsilon is 0.002 that I will put later. So now if I substitute this here, so first substitute 1 plus epsilon x square, that is 1 plus epsilon x square whole square minus 6 plus epsilon into 1 plus epsilon x1 plus 5 equal to 0. This imply 1 plus, see that we don't need the term of order epsilon square. We need only the term up to order epsilon. Okay, so we will take 2 epsilon x1 minus 6 plus 6 epsilon x1 minus 6 epsilon x1 minus epsilon. I think I am doing it right. Plus 5 equal to 0. So what you will get that this 5, this cancels because this is coming from the base solution, base state solution. Okay. This implies minus 4 epsilon x1 minus epsilon equal to 0. So x1 equal to minus 1 by 4. Okay. So what is your result then? What is your one solution then? X equal to 1 minus 0.002 divided by 4. Let me calculate this in calculator. 1 minus 0.002 by 4. So answer is 0.99995. Okay, so this is your one solution. Later, this is an quadratic equation, so we can always verify it. Okay, if the solutions are close to the correct solution or not. Now what I will do, I will substitute this in this equation. Okay, so now we want to find the expression of x1 tilde. So now it will be 5 plus epsilon x1 tilde whole square minus 6 plus epsilon 5 plus epsilon x1 tilde plus 5 equal to 0. This implies 25 plus 10 epsilon x1 tilde, because 2 into 5 into epsilon, that is 10 epsilon x1 tilde, and rest and the other term is of order epsilon squared, so we are ignoring it. So minus 30 minus 6 epsilon x1 tilde minus 5 epsilon plus 5 equal to 0. It is 25 minus 30 plus 5. This implies 4 epsilon x1 tilde is equal to, this is 4 epsilon x1 tilde equal to 5 epsilon. This implies x1 tilde equal to 5 by 4. So x equal to 5 plus 5 by 4 into 0.002. So let me calculate it. 5 plus 1.25 into 0.002. So this is 5.0025 and this is 0.495. Now what is your equation? X square minus 6.002 x plus 5 equal to 0. So x equal to minus b 6.002 plus minus 6.002 whole square minus 20 divided by 2. So let me calculate it. So 6.002 square minus 20 was 0.5. So this result is equal to 6.002 plus minus 4.0029. Okay, this is the approximated result divided by 2. Okay, so plus 6.002 divided by 5 2. So one result that I am getting from calculator is approximately equal to 5.002499, and another result is 6.002 minus 4.0029 by 2. Another result is 0.99955. So you can clearly see that this solution and this solution is really close. Okay, so the perturbation theory works. Okay, so now this is the basic idea of the perturbation technique. Okay, if you change your result, if you change the value, what will be its effect? Okay, this is the core idea of the perturbation technique, and using this you will be solving many complicated problems. Okay, so this whole course is mostly based on this perturbation technique. All right, so let me so let us solve some other examples. Okay, um, this is again from the assignment problem. Let me share the screen. Okay, so you see the first question. Okay, so what will be the correct choice of the perturbation expansion? So it is just like the last example. Okay, so the simply the perturbation, so the correct answer, you can easily see the correct answer will be option A. Okay, it will be x naught plus epsilon x naught plus epsilon for x2. So you have to expand it in this way. Okay, so this is the very trivial answer. So now the second option. Okay, so let's try. What is the choice of this? So what is the correct answer for this question? Okay, uh, so first of all, what you need to do, you can see that there are three options: A, B, C, and D. So one thing you can do very easily, that so there is something common in ABC but different in D. Can you, so what is the difference? That is the base state solution. Okay, so how to find a wasted solution? To find a wasted solution, you just need to put epsilon equal to 0, and that will give you your base state solution, right? So if you put epsilon equal to 0, what you will get? You will get the equation x cube minus 4x square plus 5x minus 2 equal to 0. Okay, so this is your base state solution. Now you just, what you need to do, so not, sorry, this is your base state equation, not solution. So now what is the equation? It is x cube minus 4x square plus 5x minus 2 equal to 0. So what are the solutions for this? Okay, if you put x equal to 2, you will find that x equal to 2 is a correct solution. And if you put x equal to 1, you will find that x equal to 1 also a correct solution. Okay, now what you have to do, exactly now the same idea. Okay, you need to expand, you need to expand the series into from two, one from two, and another from one. Okay, so if you do that, you will find, so you need, so this algebra is little bit lengthy, so if you do that, you will find that option B is your correct answer. Okay, the solutions is also already provided, so you can check that. All right, so now this question 3. So now the face portrait, the idea of face portrait, so it is already been taught to you. So okay, so let me share my tab screen again. So huh. so so if you have the equation like this, dx dt equal to some fxt, dy dt equal to some g of xt. Okay, so you find a plot of x versus y, then that is called your phase portrait. So how to do that? The very simple way is just do dy dx. So you will get some functional form. If you integrate it, if you can integrate it, you will find, you will be able to get some curve, and that will be your phase portrait. Okay, so if you have an equation like this, that d square x dt square plus omega square x equal to 0. If you have an equation like this, what is the phase portrait? So how to do that? Suppose x equal to capital X and dx dt is equal to capital Y. Okay. Uh, so we need at least two equations, right? So one equation will be dx dt equal to y, and dy dt equal to minus of omega squared x. So if you divide it, dy dx, it will be dy dx equal to minus omega square x by y. So you can very easily integrate it. It will be y square plus omega square x square equal to some constant. So what is the equation? This is the equation of an ellipse. So if you change your c, you will be able to get various ellipse. Okay, that indicates c is, so what defines this different curve? That will come from your initial condition. If your initial condition is x equal to 1, y equal to 0, you will get one curve. X equal to 1, y equal to 1 equal, you will get another curve. So as a result, you will get a bunch of curves like this. Okay, so that is your phase portrait. So from that curve, you can estimate the evolution, the dynamics of your system. Now, so now you have a system like this. Okay, and so you can see that this is a simple harmonic oscillator. For a simple harmonic oscillator, you get the equation of this ellipse. Now suppose you have equation like this. It is spiraling and it is going inward. Think physically, what is the case? So if you try to interpret it physically, so what is the example of a simple harmonic oscillator? The simple is the take the simple example, that is pendulum. If you start it from here, if there is no drag force or no viscosity, if you just leave it from here, it will travel the equal distance and then it will come back here, then it will go back and forth, and it will happen continuously. Okay, this will take this will it will, if you don't try to stop it from the Newton's first law, it will never stop. Okay, it will move with this. Now if there is viscosity, if there is some viscosity, what will, I mean, in your practical, in your day-to-day life, okay, you, what happens if you pull it, if you just do this, it will do some oscillations, the pendulum do some oscillations, then eventually it will come to rest, because air has viscosity. Okay, so air has friction, so after a few oscillation, it will eventually come to rest. Hmm? So now, when there is no viscosity, when the pendulum is just doing just this, and this, so it will be a complete cycle. So that is the case of an ellipse. But when it does this, and then finally it stops. Okay, so then what will be the result? It will be some spiral. Okay, so the spiral indicates that there is some damping. Okay, all right. Now, so remember that this is spiraling inward. If this there is damping, it is so damping, so it will finally slow down and it will be like this. But if you force it, if you give it some external forcing, okay, and if the force is increasing, okay, so what will happen? So initially it is doing like this, the pendulum, then suddenly it will do like this, and it will continuously increase, at least at the linear order. Okay, then it will look like this. It will be spiraling outward. Okay, so spiraling inwards, so that is damping. Spiraling outward, that is forcing. Okay, so these are the two extreme case, and this is another extreme case, that is no damping or no forcing. Okay, okay, so this is the idea of the phase portrait. Now, okay, now, so this is a similar kind of example we did in the last session. That is, you are provided with your equation d squared theta dt squared plus k1 theta plus k2 theta cube equal to 0. So this is your equation. Now you need to find what is the phase portrait of this oscillator. You are given that x equal to theta and y equal to theta dot. That is d theta dt. So what is the equation? So we can find it very easily. That is, so one equation will be dx dt equal to y, and dy dt equal to minus k1 x minus k2 x cube. We have done a similar example in the last class. So it will be dy dx equal to minus k1x plus k2x cube divided by y. So you substitute this, it will be y square by 2 plus k1x square by 2 plus k2 x to the power 4 by 4 equal to some constant. Okay, so this is your correct answer. Okay, so now if so now this is an interesting question, that if k1 is greater than 0, k2 is greater than 0, then what kind of motion you are expecting? So how can you analyze this? One way to analyze it, just by just by take a look at this, look at the slope from this here. You can draw the curve, and then you can just find the direction. K12 is negative, so you can just draw the So you can just draw the slopes over here. No, not from here. From here you can just draw the slopes at various point, and from that you can find your picture. Or the other way is, suppose your k2 is very small, k2 is very close to 0, so we can then neglect it. So what is the equation? Y square plus k1 x square by 2 equal to some constant. Okay, so what is the equation? It is some ellipse when k2 is small. Now if you increase k2, huh? If you increase k2, then what will happen? But k2 is positive. You will see that it will remain intact as a closed orbit, but its shape will change something like this. Okay, because why? Because if you just plot y equal to x square, y equal to x square is like this, but y equal to x to the power 4 is more flat. Okay, so that will affect your shape, but finally it will be a closed orbit. Okay, now the next question is, so another important concept for the phase portrait is the fixed point. So what is fixed point? The fixed point is the point that doesn't move. Okay, so if you start your initial if you start your initial condition at that point, so it will never move, because the system will not evolve. This is the fixed point. Now the question is, if your k1 equal to 1 and k2 equal to minus 1, okay, then what are the fixed points? So what are the equation? The equation is dx dt equal to y, and dy dt equal to, see that k1 is positive, sorry, k1 is 1 and k2 is minus 1. So dy dt equal to minus x plus x cube. Okay, so for the fixed point, dx dt has to be 0 and dy dt has to be 0. So y equal to 0 is always a solution. Another solution is x square minus x equal to 0. This implies x times x square minus 1 equal to 0. So x equal to 0, comma plus minus 1. So 0 is a fixed point, 1 0 is another fixed point, minus 1 0 is another fixed point. Okay, so this is your solution. Okay, now we can do the last big problem. Okay, so you're given that this equation d2x dt square plus 2x plus 2x cube equal to 0, and x0 equal to x naught, and dx dt t equal to 0 equal to 0. So these two are the governing. So this is the governing equation, and this is the initial condition. So you are given that xt equal to c1 cn omega t plus c2. Huh? Then find the expression, sorry, c2 comma k. Then the question is, find the expression of c1 c2 omega k using this, only this variable. Okay, because this is your only known quantity, that your initial condition. You need to find c1 c2 omega and k. Okay, so how to proceed that? The procedure is very simple, that you simply need to differentiate this. Okay, so this is your whole idea. So now let's do that. So now let me just, for the quick recap. So what is ddu of cnu equal to minus snu dnu? Okay, because we will need this thing. Okay, and what is ddu of snu? It is cnu dnu. And what is ddu of u. Yeah, so I have written it. So it is minus k square CNU into SNU. Okay, minus k square CNU SNU. Okay, so these three, we need to use these three conditions. Okay, so now let us first do what is dx dt. Dx dt. So it will be minus c1 omega Sn. So as k is constant, I will not be writing it. Okay, I will just write omega t plus c2. Sn omega t plus c2 times dn omega t plus c2. So this is your dx dt. Okay. Now we have to find what is d2x dt square equal to. So see, first I need to differentiate this. So I have to use the simple chain rule. Okay. So it will be minus c1 omega. First, I will keep this constant and differentiate this dn omega t plus c2 into what is ddu of snu, cnu, dnu. Okay, into omega into cn omega t plus c2 into dn omega t plus c2. Okay, plus now I will keep this constant Sn omega t plus c2. So what is d of ddu of dnu? It is minus k square into cnu dnu. So it is minus Sn omega t c2 plus c2 into omega into k square into cn t plus c2 times Sn omega t plus c2. Okay, equal to equal to minus c1 omega square. Let's simplify this. Okay, so this is already a very complicated expression. This d n square omega t plus c2 times cn omega t plus c2 minus sn square omega t plus c2 times cn omega t plus c2. Now I can take Cn omega t plus c2 as a common. So my c1 omega square Cn omega t plus c2 dn square minus Sn square t plus c2. Now there is a relation between dn square and Sn square. Okay. So what is the no, I am making some mistake. So it is there is a k square here. So what is the relation? The relation is k square Sn square u plus dn square u equal to 1. So you can write it as minus c1 omega square cn omega t plus c2. So it will be 1 minus 2k square Sn square omega t plus c2. Now what is Sn square? Sn square is 1 minus cn square, right? So it will be minus c1 omega square cn omega t plus c2 will be 1 minus 2k square plus 2k square cn square omega t plus c. Okay, yeah. So now, so if I take this on the right hand side, I will get that. So now I can write cn omega t plus C2 equal to X. Just a second. Oh, so here it is d2x dt square, right? Right. Okay. So now C1 times Cn omega 2 omega t plus C2 is X. Okay. So d2x dt square plus C1 omega square times 1 minus 2k square Cn omega t plus C2 plus 2k square omega square into C1 Cn cube C2 equal to 0. So if I use this expression, I will get plus 2k square omega square by square x cube equal to 0. Now compare it with the expression d2x dx dt square plus 2x plus 2x cube equal to 0. So what we are getting? We are getting omega square k square by c1 square equal to 1. This implies omega square k square equal to c1 square and omega square into 1 minus 2k square equal to 2. Okay. So but I have some other relations. Okay. So what is the relation? That is x of 0 equal to 1 and x dot of 0, sorry, x dot of 0 is equal to your 0. Okay. So now what is x0? X0 is c1 cn omega t plus c2. So c2 comma k equal to x naught. Hmm? And x dot equal to 0. So what is x dot? X dot will, so it will be minus c1 sn c2 comma k dn c2 comma k equal to 0. Now from the definition we have Sn u equal to y, Cn u equal to x by a. Now when your u equal to 0, then Sn of 0 equal to 0, Cn of 0 equal to 1. So I can write this expression as C2 equal to 0, C1 equal to x naught. Okay, so this is one solution for this expression. Okay, C2 equal to 0, C1 equal to x naught. If you put it, you will find that this is a solution. There can be some, there I'm not sure, but there can be some other solution, but you need to check that. But for this is obviously a solution. Okay, so now so what are the answers that you are getting? That is C1 equal to x naught and C2 equal to 0. Okay, so now if you substitute it here, so if you substitute it in this expression, so you have two expressions. One is omega square k square is equal to C1 square. And what is C1? C1 is your x0. So omega square x square equal to x naught square. So, and another option is this expression, that is omega square into 1 minus 2k square equal to 2. Equal to 2. So I can use this expression here, that is omega square minus 2 omega square k square equal to 2. This implies omega square equal to 2 into 1 plus x naught square. So omega equal to square root of 2 1 plus x naught square. And for omega is square root of 2 or x naught square, what will be your k square? K square equal to x naught square divided by 2 into 1 plus x naught square. So k equal to square root x naught square by 2 into 1 plus x naught square. So what are the solutions? If you there were initially four constant. So what was the expression? Your expression was x of t equal to c1 cn omega t plus c2 comma k. C1 was a constant, omega is a constant, c2 is a constant, k is also a constant. Okay, and you are provided with only two information, that is x of 0 equal to x naught and x dot of 0 is 0. Okay, you are provided with only this expression, this information. Okay, and finally now you have found that your c1 equal to x0, c2 equal to 0, omega equal to square root of 2 into 1 plus x naught square, and k equal to x naught by square root 2 into 1 plus x naught square. Now, can you see one interesting feature? So, remember the simple pendulum. Okay, for the simple pendulum, what was the frequency? Omega equal to square root of g by L. Okay, but in the class it was shown that when your when your initial perturbation is large, that means your initial angle theta is not small, then your frequency depends upon the initial amplitude. Okay, obviously, because if your amplitude is large, then your frequency is also large. Okay, so this is the feature of the nonlinear problem. Okay, so this is essentially the feature of your the nonlinear problem. Okay, so now, but uh, but what about the linear solution? Linear solution doesn't say anything. The linear solution just say that if you initially perturb it by suppose say 4 centimeter, if I calculate the horizontal distance, or 8 centimeter, or 2 centimeter, okay, they all will oscillate with the same frequency. But that is absurd, right? Because if you but you can see it, but because when you perturb it by a significant amount, the oscillation will be much faster. Okay, so here in this way you can see that your oscillation, if this is a say if this is a if the system is a linear system, okay, then your frequency would have been square root of 2. Why? Because if the system is linear, then this term will disappear. This term is what making it non-linear. And the expression and apart from this term, this is simply d2x dt square plus 2x. So the frequency is square root of 2. Okay, but this term is making it non-linear, and you can see because of the presence of this nonlinear term, your frequency is influenced by your initial displacement x naught. Okay, now if you are told to calculate that time period of this, you will see that your time period will not be constant. It will, I mean, it is in a sense it is constant, but it is also it will also depend on your initial position. It will be a simply 2 pi by omega. It will be 2 pi by square root of 2 into 1 minus x naught square. Okay, so this will be a time period for that. Okay, this is non-linear time period. Just a moment. So, so just for us, okay. So this was the last problem that I wanted to solve today. So just let's go through the topics that we have covered this today. So from the next class onward, we will see some complicated technique in the perturbation, some complicated method in the perturbation techniques. Okay. So today's class was mostly based on the Jacobi elliptic function. Okay. So this is a new thing that you are learning. This is a completely new thing, and so what we have solved, that we have solved some identities which are similar to the trigonometric identities that we learned in our class 2 courses, and we have seen some the derivative of those elliptic function. Okay. And then the we have seen the use how to use the elliptic integration in some practical problem. Okay. And after that we have solved some complicated problems. So this is the example. So this is one of the complicated problem using this Jacobi elliptic function. and and then this is the so we have also started the perturbation technique. Okay. So this is so you will see that that the use of this Jacobi elliptic function, they will give you accurate result, but but as you can see that the calculation is very complicated. Okay. So later you will see that we will solve a similar problem, that is d2x dt square plus k1x plus k2x cube equal to 0, a problem like this using simple perturbation technique. Okay, this can be solved completely by the Jacobi elliptic function, but we will be able to solve it using the perturbation technique, as you will see it. Okay. So what I will do, I will record this updated lecture. I have recorded this lecture and I will post it. I will post it in my YouTube channel, and I will share this PDF document with you. Okay, so let's meet in the next class, and good night.